Hello there, and welcome to Sleepy Science Vault. Somewhere beneath your feet, right now, there is a planet quietly keeping time. Not in seconds or hours, but in something far larger, in the slow turning of geological ages, in the patient burning of a star 93 million miles away. Tonight, we are going to step back from the present moment and look at Earth not as a fixed and permanent home, but as a living process, a process with a beginning, a middle, and yes, eventually, an end. This is a story told in billions of years. It is not frightening. It is not urgent. It unfolds so slowly that entire epochs of life will rise and fall within it, the way single days rise and fall within a human life. Think of this less as a warning, and more as a long, quiet look at the deep future, the kind of future that only geology and starlight can measure. So settle in. Let your mind loosen its grip on the ordinary scale of hours and days. Tonight we are thinking in eons. Let's begin with where Earth actually stands, right now, in its own story. Our planet is approximately 4.5 billion years old. It formed out of a swirling disk of dust and gas around a newly ignited sun, cooling slowly from a molten sphere into the layered, rocky world we know today. Oceans, continents, an atmosphere thin and blue against the black of space. 4.5 billion years is already an almost incomprehensible stretch of time. If you tried to count one number every second, without stopping, day and night, it would take you over 140 years just to reach 1 billion. And Earth has lived through 4.5 of those. But here is the quietly astonishing part. Earth is not just old, it is, in a very real sense, already old relative to how long it has left. Scientists estimate that Earth's total habitable lifespan, from formation to the point where conditions become truly hostile to life as we know it, may only stretch to around 5.5 billion years total. Which means the planet we are standing on right now has already used up roughly 82% of its expected lifetime. Let that settle for a moment. 82%. If Earth's story were a single day, beginning at midnight, we would already be deep into the evening, past dinner, past sunset, moving steadily toward the later hours of the night. Not near the very end, not yet, but well past the midpoint, well past the peak of the afternoon. There is still time left. A great deal of time, by any human measure. But the arc of the story has already bent toward its later chapters. This is a strange thing to sit with. Because everything around us, the mountains, the oceans, the forests, they all feel eternal. They feel like the backdrop of time, rather than characters within it. But Earth is not a backdrop. It is a participant. It has a lifespan, just as surely as a tree does, or a star does, or a person does, only measured in a unit of time so vast that it dwarfs every human civilization that has ever existed, stacked one on top of another. So what actually brings a planet's habitable years to a close? For Earth, the answer begins not with the planet itself, but with the star it orbits. The sun is not static. It is not the same steady, unchanging light that our ancestors saw 10,000 years ago, even though to our eyes it appears constant, day after day, rising and setting in perfect rhythm. In truth, the sun is very slowly, very gradually, growing brighter. This happens because as a star like our Sun burns through its hydrogen fuel, converting it into helium at its core, the core itself becomes denser and hotter, and the star responds by increasing its overall luminosity, ever so slightly, over enormous stretches of time. This process has been happening since the Sun was born, and it will keep happening for billions of years yet to come. And crucially, long before the Sun ever swells into the dramatic, sky-filling red giant that so many people picture when they think about the Sun's eventual fate, this slow, steady increase in brightness will already be reshaping conditions here on Earth. The red giant phase, the truly explosive final act of the Sun's life, is still roughly 5 billion years away. But the effects of a brightening Sun begin arriving far, far sooner than that. This is one of the more counterintuitive truths in planetary science. Most people imagine Earth's story ending in one single, dramatic event, the Sun expanding, swallowing the inner planets, a fiery finale. But the real story is quieter, and in some ways more poignant. Earth's hospitality to life is expected to fade gradually, over hundreds of millions of years, long before that final stellar drama ever begins. The ending, it turns out, is not a single moment. It is a slow fading of the light, in more ways than one. Which brings us to a timeline that might surprise you. Current models suggest that Earth will likely stop being hospitable to Earth-like life several billion years before the Sun ever reaches its red giant stage. Not shortly before, billions of years before. The window for complex, familiar life on this planet is expected to close long before the Sun's final transformation ever begins. This means that if you imagine the Sun's red giant phase as the closing curtain of the theater, Earth's story as a living world may actually end much earlier in the performance, somewhere in the second half, well before the final scene. The habitability of Earth, in other words, is not simply a countdown to the Sun's death. It is its own, separate, earlier deadline, set not by the Sun's ultimate fate, but by the subtler, earlier consequences of its slow brightening. It's worth pausing here, just for a moment, to notice how different this is from the popular imagination of Earth's end. There is no single, sudden catastrophe waiting for us on the calendar of deep time. There is, instead, a long, gradual drift, conditions shifting so slowly that within any single human lifetime, or even across 1,000 human lifetimes, absolutely nothing would seem to change at all. Let's look now at one of the more delicate, and strangely moving, details in this story, the fate of our moon, and something it currently allows us to witness. Right now, in our sky, we experience a truly remarkable coincidence. The Sun is about 400 times larger than the Moon, and yet, by sheer chance, it is also roughly 400 times farther away. This ratio is so precise that, from Earth's surface, the Sun and Moon appear almost exactly the same size in the sky. And this coincidence is the only reason total solar eclipses are possible, those breathtaking moments when the Moon passes perfectly in front of the Sun, blotting out its light entirely, revealing the ghostly white corona shimmering around a perfect black disk. But this coincidence will not last forever. The Moon is slowly moving away from Earth. It has been doing so since its formation, drifting outward at a rate of about 3.8 centimeters per year, a consequence of the gravitational tug-of-war between Earth's oceans and the Moon's orbit. It is an almost imperceptibly slow drift. A few centimeters a year is less than the length of your finger. But slow processes, given enough time, produce enormous change. Scientists estimate that within about 600 million years, the moon will have drifted far enough away that it will simply be too small, too distant, in our sky to ever fully cover the sun again. The precise alignment that makes total solar eclipses possible will be gone. Total solar eclipses will stop happening. Forever. There is something quietly moving about this fact. Every total solar eclipse that has ever been witnessed, by ancient astronomers lying on hillsides, by medieval scholars recording omens in the sky, by modern travelers chasing the path of totality across continents, every single one of those experiences belongs to a finite, limited chapter in Earth's much longer story. We happen to be living inside that chapter. 600 million years from now, whatever inhabits this planet, if anything does, will look up during a solar eclipse and see only a dark disk with a bright, uncovered ring of sunlight around it, a partial eclipse, forever. The perfect black circle, the shimmering corona, that particular kind of celestial theater, will simply no longer be possible. It is a small, cosmic reminder that even the sky above us is not permanent. It, too, has a season. Now let's turn back to the atmosphere, and to a debate that is still very much alive among scientists, the question of exactly when Earth's runaway greenhouse era begins. One influential model suggests that this runaway greenhouse state, a point where the atmosphere traps heat in an accelerating, self-reinforcing cycle, may not fully arrive for another 600 to 700 million years. This is a slightly different figure than some other estimates, and that difference matters, because it reflects something important about how science actually works. These are not settled facts, carved in stone. They are careful, evolving models, built from our best current understanding of solar physics, atmospheric chemistry, and planetary history, models that get refined and adjusted as new data arrives. So when we talk about Earth's future, we are not reciting a single, fixed prophecy. We are describing a range of carefully reasoned possibilities, offered by researchers who have spent their careers trying to understand how stars age, and how planets respond. Different models, using different assumptions, arrive at slightly different numbers. But almost all of them agree on the broad shape of the story: a slowly brightening sun, a gradually warming Earth, and eventually, a tipping point beyond which the warming becomes self-sustaining and irreversible. And that tipping point may require less of a nudge than you'd expect. Some research suggests that it would take only about 6% more sunlight than Earth currently receives to push the planet into a runaway greenhouse state. 6%. Not 60. Not 600. Just 6. To understand why such a small increase could have such an enormous effect, it helps to understand what a runaway greenhouse actually is. As sunlight increases, the oceans warm, and warmer oceans evaporate more water vapor into the atmosphere. Water vapor is itself a powerful greenhouse gas, so more of it in the atmosphere traps even more heat, which warms the oceans further, which releases even more water vapor. It is a feedback loop, one that, once it passes a certain threshold, can no longer reverse itself. The warming feeds the warming. And eventually, the oceans themselves begin to boil away into space, and the surface becomes the kind of blistering, lifeless world we see on Venus today. Given how slowly the sun brightens, year over year, that 6% threshold is not something we need to worry about on any human timescale. It lies hundreds of millions of years in the future. But it is worth noticing just how narrow the margin is, in the grand cosmic sense. Earth's comfortable, life-supporting window is not some enormous, forgiving range of temperatures and conditions. It is a fairly narrow band, one that a star only needs to nudge slightly to close. There is another, quieter thread arriving on a similar timescale, not too much heat, but too little of something else entirely. Sometime between roughly 600 million and 800 million years from now, models suggest that atmospheric carbon dioxide could fall below 10 parts per million. That may sound like a strange kind of danger. We tend to think of rising carbon dioxide as the atmospheric problem to worry about, but on this particular deep time scale, the opposite trend becomes the real concern. Here is why. As the sun brightens, weathering rates on Earth's surface increase. Rain becomes slightly more intense, chemical reactions between rainwater and exposed rock accelerate, and this process pulls carbon dioxide out of the atmosphere at a faster and faster rate, locking it away in rock formations. Over hundreds of millions of years, this steadily drains the atmosphere of one of its essential ingredients. And that ingredient is essential, because plants need it. Specifically, the vast majority of plant life on Earth today, the grasses, the trees, the shrubs, nearly all the greenery that blankets this planet, relies on a particular photosynthetic pathway known as the C3 pathway. And C3 photosynthesis simply cannot function once atmospheric carbon dioxide drops below that critical threshold of around 10 parts per million. Below that point, these plants can no longer convert sunlight into usable energy. They cannot survive. So picture this, slowly unfolding across hundreds of millions of years. Forests thinning, grasslands retreating, the deep green tapestry that currently covers so much of Earth's land gradually fading, not from heat or drought in the way we usually imagine, but from the slow, invisible starvation of a shrinking atmospheric ingredient. It is one of the more haunting details in this entire story, the idea that plant life, the very foundation of Earth's food chains, may falter not because the world becomes too harsh in an obvious way, but because one quiet chemical balance, present in only trace amounts to begin with, slips below the line it needs to survive. This same brightening sun, this same slow warming, also threatens to disrupt something even more fundamental to how Earth regulates itself over deep time, a process known as the carbonate-silicate cycle. This cycle is, in many ways, Earth's long-term thermostat. Volcanic activity releases carbon dioxide into the atmosphere. Rainfall and weathering pull that carbon dioxide back out, converting it into carbonate rocks. Those rocks eventually get carried into the ocean, subducted beneath tectonic plates, and recycled back into the mantle, where the carbon can eventually be released again through future volcanic activity. Round and round it goes, a slow, patient exchange between atmosphere, ocean, and rock, keeping Earth's carbon levels, and by extension its climate, in a rough, self-correcting balance across hundreds of millions of years. But as the sun brightens and weathering accelerates, this cycle begins to be pushed out of its natural rhythm. Carbon dioxide gets pulled from the atmosphere faster than volcanic activity can replace it. The delicate feedback loop that has helped stabilize Earth's climate for billions of years starts to falter, not break instantly, but drift, slowly, out of its long-held equilibrium. And this disruption may not stay contained to the atmosphere alone. Some researchers believe that as this cycle breaks down, and as the mantle itself continues its own long-term cooling, the very engine driving plate tectonics could begin to slow. Plate tectonics, that grand, ongoing shifting of continents, the process that builds mountain ranges and opens ocean basins and recycles Earth's crust over hundreds of millions of years, may itself gradually wind down, and eventually, stop. It's a remarkable thought to end on for now. We tend to think of the ground beneath us as the most stable, unchanging thing in our lives, solid, motionless, eternal. But even the tectonic plates, those vast slabs of rock drifting so slowly across the planet's surface that we never feel them move, are themselves part of this larger unfolding story. They, too, are running on borrowed time, tied to a cycle of carbon and rock and heat that stretches back to Earth's molten beginnings, and forward, into a future shaped by a star that simply cannot stop getting brighter. We have only just begun tracing this long arc forward. There is still so much more of Earth's future left to explore, more shifts in the atmosphere, more changes to the oceans, more turning points still waiting quietly out there in the deep unfolding of time. For now, let this first stretch of the story settle over you gently, the slow brightening of a star, the drifting of a moon, the quiet fading of an atmosphere. Let your thoughts rest in that vastness for a while, as we continue on, into the next set of facts, and the next chapter of Earth's long, unhurried ending. Picture, for a moment, what happens when that grand recycling engine we just described begins to falter, when the volcanoes that have spent billions of years replenishing the atmosphere start to fall silent, one by one, across the planet's surface. Carbon dioxide has always existed in a delicate balance on Earth. It gets pulled out of the atmosphere by rainfall and rock weathering, and it gets put back in by volcanic outgassing, deep from within the planet's molten interior. It's a cycle that has run continuously since Earth's earliest days, quietly stabilizing the climate across immense stretches of time. But as we just explored, this cycle depends on active geology, on volcanoes that still have the heat and the pressure to push gases up through the crust. Without that ongoing volcanic contribution, the whole balance tips permanently in one direction. Weathering keeps pulling carbon dioxide out of the air, but nothing significant replaces it. And so, gradually, relentlessly, atmospheric CO2 levels continue their long decline, falling further and further, until they simply cannot support the C3 plants that make up the overwhelming majority of Earth's plant life today. It's worth sitting with the strange quiet of this particular ending. No explosion, no sudden event, no single dramatic turning point that anyone could point to and say, "This is when it happened." Just a slow, patient drawdown, decade by decade, millennium by millennium, of the very gas that green and growing things need to build their bodies out of sunlight. This raises a bigger question, one that scientists have been trying to answer with increasing precision in recent years. Given everything we've just described, the brightening sun, the disrupted carbon cycle, the slowing of plate tectonics. How much longer, exactly, does complex life have left on this planet? The answer depends quite a bit on which model you're looking at, and what specific mechanism each research team focused on. One detailed study, examining the long-term trajectory of atmospheric carbon dioxide, suggests that complex eukaryotic life could disappear from Earth in roughly 1.3 billion years, once CO2 becomes too scarce to sustain the plant life that anchors the rest of the food chain. Eukaryotic life, for context, refers to any organism made of cells that contain a nucleus, which includes essentially every plant, animal, and fungus we know, along with countless single-celled organisms. It is, in other words, nearly all of the complexity we currently associate with life on Earth. And this particular model suggests that within 1.3 billion years, the conditions required to sustain that complexity may simply no longer exist. But that's only one piece of the puzzle. Because carbon dioxide isn't the only ingredient at risk. Another recent estimate takes a different approach entirely, focusing not on carbon but on oxygen, and arrives at an even shorter timeline. This model suggests that complex life on Earth could effectively end in about 1 billion years, driven by a gradual, long-term decline in atmospheric oxygen levels. This might feel surprising, given that oxygen levels have actually been remarkably stable, and even increased, over hundreds of millions of years of Earth's more recent history, ever since photosynthetic life first began pumping oxygen into the atmosphere billions of years ago. We tend to think of oxygen as one of the more secure, dependable features of our planet's air. But researchers modeling the far future point out that this stability depends entirely on a thriving biosphere, on vast populations of photosynthesizing organisms, on land and in the oceans, continuously producing oxygen faster than it gets consumed or chemically locked away in rock and sediment. Once that photosynthetic activity begins to decline, as rising temperatures and dwindling carbon dioxide put increasing stress on plant life and ocean phytoplankton alike, oxygen production slows correspondingly. And oxygen, unlike some atmospheric gases, doesn't just linger indefinitely once its source dries up. It gets absorbed by weathering rock, dissolved into oceans, consumed by various chemical processes throughout the Earth system. Without a steady biological source continuously replenishing it, atmospheric oxygen would begin a slow, and eventually quite dramatic, decline. This particular model paints a striking picture of the deep future, an Earth where the atmosphere doesn't just warm and dry, but literally loses one of the specific ingredients that most complex organisms, including nearly every animal alive today, absolutely require to survive. An Earth where breathing, in the way we understand it now, simply stops being possible for the vast majority of species. Taking these different threads together, the decline of carbon dioxide, the disruption of the carbon cycle, the eventual drop in oxygen, a broader picture emerges. One frequently cited estimate suggests that Earth may become unlivable for the vast majority of organisms in roughly 1.3 billion years. And notice how far in advance of the Sun's dramatic red giant transformation that figure sits. 1.3 billion years, compared to roughly 5 billion years until the red giant phase begins. This means Earth's era of rich, complex, abundant life may end well over 3 billion years before the Sun ever undergoes its own final, spectacular transformation. It's a humbling recalibration of the story. We often imagine Earth's fate as tied directly to the Sun's most dramatic moment, the expansion into a red giant that eventually engulfs the inner planets. But according to these models, that final stellar drama may unfold across a largely empty stage, a planet that has already, for billions of years, been silent of the kind of complexity we associate with life today. Now, it's important to say clearly, science does not speak with one single voice on exactly when this transition happens. And that's not a weakness in the research. It's simply the honest, careful uncertainty that comes with modeling systems this complex, this far into the future. A separate, independent climate modeling study, using different assumptions about cloud behavior, ocean heat absorption, and atmospheric feedback loops, arrives at a noticeably more optimistic figure. This research suggests Earth may retain the ability to support life for at least 1.5 billion years, a full 200 million years longer than some of the more conservative estimates we just explored. Why the difference? Partly, it comes down to just how sensitive our climate models are to small variations in assumptions about cloud cover, ocean depth, and heat capacity, and the precise pace of the carbon cycle's decline. Predicting global climate even a century into the future involves genuine complexity and uncertainty, as anyone who follows modern climate science already knows. Now imagine extending that same kind of modeling not 1 century, but well over 1 billion years into the future. Small differences in initial assumptions can compound, over such enormous timescales, into meaningfully different outcomes. So rather than thinking of these various figures, 1 billion years, 1.3 billion years, 1.5 billion years, as competing, contradictory claims, it may help to think of them the way you'd think of a weather forecast with a wide margin of uncertainty. They're not disagreements about whether this transition happens. Every model agrees that it does. They're careful, evidence-based attempts to narrow down when, using the best tools and data currently available. And as our understanding of planetary atmospheres, cloud physics, and deep time geology continues to improve, these estimates will keep being refined, sharpened, adjusted, slowly converging, perhaps, toward a more precise answer. Let's step further out now, into a time frame where the different models begin to agree more closely, a point roughly 2 billion years from now, when an entirely different kind of transformation is expected to take hold. By that point, scientific models suggest the Sun will be shining approximately 20% brighter than it appears to us today. 20% might not sound dramatic on its own. But remember, earlier in our story, we learned that an increase of just 6% could be enough to trigger a runaway greenhouse effect. 20% brighter sunlight, arriving on a planet whose natural cooling systems, its carbon cycle, its plate tectonics, its lush carbon dioxide absorbing plant life, have likely already broken down, represents an entirely different order of environmental stress. Under these conditions, models suggest the oceans themselves may begin to evaporate. Not gradually recede at the edges, the way a drought might shrink a lake, but truly, planet-wide, evaporate, water vapor rising in ever greater volumes into an atmosphere already thick with heat-trapping gas, in a self-reinforcing cycle that becomes progressively harder to stop. There is something almost dreamlike, in a haunting sort of way, about picturing Earth's oceans slowly lifting into its sky. The blue that has defined this planet's appearance from space since long before complex life ever emerged, that deep, endless blue that separates Earth so visibly from its rocky, arid neighbors, gradually thinning, gradually rising, gradually disappearing from the surface it once defined. And once again, notice how far ahead of schedule this all occurs, relative to the Sun's ultimate transformation. 2 billion years for the oceans to begin evaporating. Roughly 5 billion years before the Sun becomes a red giant. Earth's watery, blue identity, the very feature that makes it look so distinctly alive from the vantage point of space, is expected to fade less than halfway through the Sun's remaining lifespan as a stable, main-sequence star. This is, in many ways, the central theme quietly running beneath every fact we've explored so far tonight. Earth doesn't need the Sun's death to become uninhabitable. It only needs the Sun to keep doing exactly what it's already doing, slowly, steadily, brightening. That gradual increase in luminosity, so gentle and gradual that it registers as nothing at all across a single human lifetime, or 100 human lifetimes, accumulates over hundreds of millions and billions of years into changes that reshape the entire character of this planet, long before its final chapter with the Sun ever begins. There's a particular number that appears again in some of the more detailed modeling of Earth's far future, a number that helps make this abstract, distant warming feel a bit more tangible. Some estimates suggest that Earth's global mean temperature could eventually climb to somewhere around 100 degrees Celsius. The boiling point of water, at sea level pressure, blanketing the entire globe, as an average condition rather than an extreme one. At that kind of sustained temperature, liquid water on the surface simply cannot persist in any stable, lasting way. The oceans that once covered roughly 70% of this planet's surface, that gave rise to the earliest life billions of years ago, that have shaped Earth's climate, its geology, its very identity as a world, would no longer be able to exist in their familiar, liquid form. And what happens to that water doesn't simply vanish without consequence. During this runaway greenhouse phase, as ocean water evaporates into the atmosphere in ever greater volumes, much of that water vapor eventually makes its way to the upper atmosphere, where intense solar radiation breaks the water molecules apart, splitting them into hydrogen and oxygen. And here's the part that quietly seals the outcome. Hydrogen, being the lightest of all elements, can drift high enough into the outer atmosphere to be slowly, steadily lost to space entirely, carried off by the solar wind, escaping Earth's gravity for good. This is not a process that could ever reverse itself. Once that hydrogen escapes into space, it's gone, permanently, no longer available to recombine into water molecules, no longer part of Earth's system in any way. It represents, in the most literal sense, the slow, irreversible loss of the very substance that made this planet a suitable home for life in the first place. There's something profoundly poignant in tracing this particular thread all the way through. Water arrived on Earth billions of years ago, likely carried here by ice-laden comets and asteroids during the solar system's chaotic early history. It pooled into oceans, it enabled the first stirrings of life, It carved canyons and nourished forests and filled the clouds that have painted every sunset any human being has ever witnessed. And billions of years from now, that same water, molecule by molecule, may rise into the sky one final time, not to fall again as rain, but to break apart entirely, drifting off into the vast, silent dark of space, leaving behind a planet that no longer holds the one substance that made it so remarkably, improbably alive. We'll continue tracing this long unraveling in the chapters ahead, following the story further still, into the ages when Earth's surface begins to resemble something almost unrecognizable from the world we know now. For the moment, let this settle quietly in your mind: the fading green of forests without enough carbon to breathe, the thinning of oxygen across a billion patient years, and the slow, silent rise of an ocean lifting itself, one last time, into the sky. Let's return to that image we left off with, water rising into the sky for one final time. Because that process, once it begins in earnest, doesn't happen all at once. It unfolds gradually, across an almost unimaginable stretch of time, and it sets off a chain reaction that touches nearly every system on the planet. As the oceans continue evaporating, more and more water vapor accumulates in the upper atmosphere, far above the clouds we're familiar with, in a region exposed directly to the harshest of the sun's ultraviolet radiation. And up there, that radiation does something quietly permanent. It breaks apart the water molecules themselves, splitting each one into its two basic components, hydrogen and oxygen. The oxygen, being heavier, tends to stay closer to the planet, reacting with surface rock and other elements. But the hydrogen, light as it is, drifts higher still, until eventually it escapes Earth's gravity altogether, lost to the emptiness of space. This is, in a sense, the planet slowly forgetting how to hold on to its own water. Molecule by molecule, over unimaginable stretches of time, the raw material of Earth's oceans is drawn upward and stripped away, never to return. It is one of the more literal ways a planet can lose its habitability, not through some single catastrophic blow, but through this slow, patient disassembly, happening one water molecule at a time, for millions upon millions of years. And as this evaporation and atmospheric stripping continues, the runaway greenhouse effect we described earlier doesn't simply plateau. It intensifies. With so much heat-trapping water vapor filling the atmosphere, and with the sun continuing its slow climb in brightness, surface temperatures on Earth are expected to climb to truly extraordinary levels high enough, according to some models, to begin melting the surface of the planet itself. Try, for a moment, to picture that. Not lava flowing from a volcano, but entire regions of ordinary surface rock, heated so intensely and so relentlessly by a thickening, superheated atmosphere, that they begin to soften, and eventually liquefy. The solid ground that has defined this planet's surface for over 4 billion years, slowly losing its solidity, becoming, in places, something closer to what Earth looked like in its very earliest, molten infancy, right after formation. It is a strange kind of symmetry, a planet that began as a glowing ball of liquid rock, and may end, billions of years later, drifting back toward that same state, closing the loop on its own long story. Long before conditions reach that extreme, though, there's an earlier and in some ways more immediate collapse taking place, one centered not on rock, but on the plants. As atmospheric carbon dioxide continues its long decline, and as temperatures climb beyond what most plant life can tolerate, plants are expected to be among the very first casualties of this unfolding transformation. And because nearly all of Earth's atmospheric oxygen is ultimately produced through photosynthesis, generated by plants on land and phytoplankton in the ocean, the disappearance of plant life sets off an immediate and severe consequence. Oxygen levels begin to fall sharply. It's worth pausing on just how fundamental this connection really is. Every breath of oxygen that has ever filled human lungs, every breath taken by every animal that has ever lived on this planet, ultimately traces back to photosynthesis, to the quiet, tireless work of plants and algae, converting sunlight and carbon dioxide into the very oxygen that animal life depends on to survive. It is one of the most elegant and essential partnerships in the story of life on Earth, plants and animals locked in a kind of breathing rhythm with one another, across hundreds of millions of years. But partnerships like this only hold as long as both sides remain intact. Once plants begin dying out on a global scale, unable to survive in a carbon-starved, overheated atmosphere, that steady supply of oxygen begins to dwindle right along with them. There's no backup system, no alternate source capable of replenishing oxygen at anywhere near the scale required to sustain complex animal life. As the plants go, so eventually goes the air itself. This leads to what may be one of the more sobering thresholds in this entire unfolding story. As oxygen levels continue their decline, they eventually fall below the level required to sustain any kind of animal life as we currently understand it. Not just large animals, not just the more sensitive or specialized species, but animal life in general, the kind of aerobic respiration that underlies essentially every animal on Earth today, from the smallest insect to the largest whale. It is a quiet, almost invisible kind of ending. No dramatic extinction event, no asteroid, no sudden catastrophe. Just a slow, steady thinning of the very air that animal life has always depended on, continuing gradually, generation after generation, until breathing, in the way every animal alive today understands it, simply stops being possible anywhere on the planet's surface. Between the loss of the oceans, evaporating and drifting away into space, and the loss of a breathable atmosphere, thinned first by the collapse of plant life and then further transformed by the runaway greenhouse effect, the conditions that once made Earth such a remarkably hospitable world are expected to unravel almost entirely. And together, these two losses, water and air, mark what many scientists consider the effective end of complex life on Earth as we currently know it. Not the end of the planet itself. Not necessarily the end of all life in every microscopic form. But the end of the rich, complex, oxygen-breathing, water-dependent biosphere that currently blankets this world. So what, then, does Earth actually look like, once this transformation runs its full course? For an answer, we don't necessarily need to imagine something entirely without precedent. We can look, instead, to a neighboring world that has already lived through a strikingly similar transformation. Venus. Some models suggest that by around 3.5 billion years from now, Earth's surface conditions may closely resemble those found on Venus today. And Venus offers a genuinely vivid picture of what that might mean. a surface temperature of roughly 460 degrees Celsius, hot enough to melt lead. An atmosphere composed almost entirely of carbon dioxide, crushingly thick, with surface pressure over 90 times greater than what we experience here on Earth. Thick, permanent clouds of sulfuric acid, drifting endlessly overhead, blocking any direct view of the surface below. No oceans. No liquid water of any kind. A world that likely once had oceans of its own, billions of years ago, before its own runaway greenhouse effect stripped them away entirely. Venus, in other words, may not simply be a strange, alien neighbor, fundamentally different from our own planet. It may be something closer to a preview, a glimpse, from across the solar system, of a transformation that Earth itself is expected to eventually undergo. Two planets, formed from similar material, at a similar distance from the same star, following remarkably similar paths, just offset from one another by billions of years of timing. It's a genuinely striking thought, the next time Venus happens to be visible, low and brilliant on the horizon just after sunset or before sunrise. That brilliant point of light isn't simply a distant, alien world, unrelated to our own. In a very real sense, it may be showing us our own future, playing out just a bit further along its own particular timeline. Now, it's important to note that Earth's eventual transformation may not perfectly mirror Venus in every detail. Some models suggest Earth could end up with an atmosphere every bit as thick and hostile as Venus's, choked with carbon dioxide and heat-trapping gases. Other models suggest a different possibility entirely, that instead of retaining a thick atmosphere, Earth might eventually lose most of its atmosphere altogether, stripped away gradually by solar radiation and the ongoing loss of key atmospheric gases, leaving behind something closer to a bare, scorched, largely airless world. Either path leads to the same fundamental outcome, a planet no longer capable of supporting anything resembling the rich, complex biosphere we know today. But the specific character of that transformation, whether Earth ends up shrouded and crushed beneath a thick, Venus-like atmosphere, or stripped bare and largely airless, remains an open and genuinely fascinating question in ongoing research. This uncertainty points to something important, something worth carrying with us as we continue further into this story. Earth's ultimate fate isn't determined by the sun alone. It's true that the sun's slow, steady brightening sets the entire process into motion, providing the fundamental driving force behind nearly everything we've discussed tonight. But how exactly that process plays out, how quickly it unfolds, and what Earth specifically ends up looking like on the other side of it, depends just as much on Earth's own internal chemistry and geology. The precise composition of Earth's crust. The specific rate at which carbon dioxide gets drawn out of the atmosphere through weathering. The particular chemical makeup of the rocks that make up the ocean floor and continental plates. All of these Earth-specific details shape the story just as powerfully as the sun's light does. Earth's future, in other words, isn't simply a passive story of a planet being acted upon by an external star. It's a genuine collaboration between solar physics and planetary chemistry, between the light arriving from 93 million miles away, and the intricate, particular geology found right here, in the rock and soil beneath our feet. And this connection between surface chemistry and solar brightness runs deeper still, extending all the way down into the planet's molten interior. Because ultimately, how long Earth continues to display active geology, volcanic activity, plate tectonics, the whole intricate system of processes that continuously reshape the surface and regulate the long-term carbon cycle, depends heavily on how quickly Earth's interior itself continues to cool. Earth's core has been slowly losing heat since the planet's formation, 4.5 billion years ago, and that heat is precisely what powers mantle convection, the slow, churning movement of molten rock deep underground that in turn drives the movement of tectonic plates across the surface above. As that internal heat continues to gradually dissipate, radiating outward into space over the coming billions of years, the engine driving plate tectonics is expected to weaken correspondingly. And once that engine eventually stops altogether, the volcanic activity we've discussed throughout tonight's story, the very process responsible for replenishing atmospheric carbon dioxide and keeping Earth's long-term climate in balance, stops right along with it. So Earth's future, it turns out, is really being written from two directions at once. From above, through the slow, inexorable brightening of the sun. And from below, through the gradual, equally inexorable cooling of Earth's own molten heart. Two separate clocks, ticking at entirely different rhythms, both counting down toward the same eventual destination. There's something quietly beautiful in recognizing that. This isn't simply a story about a star growing older and brighter, imposing its will on a passive, unchanging planet below. It's a story about two processes unfolding together, in a kind of slow, patient dialogue that stretches across billions of years, the fire above, and the fire below, each shaping, and being shaped by, the other, until eventually, together, they close this particular chapter of Earth's long and remarkable story. We'll carry this thread forward together, into the chapters still ahead, following Earth's transformation further still, toward the more distant and even more dramatic turning points that still lie waiting, deep in the folds of time. For now, let yourself rest here a while, in this quiet image of two flames, one high above in the brightening sun, one buried deep beneath our feet in the cooling earth, both burning steadily onward, toward a future so far away that it exists, for now, only in the patient calculations of careful scientists, and in stories like this one, told softly, in the dark, for anyone still listening. We left off in that quiet image of two flames, one above, one below, both slowly shaping Earth's distant future together. Let's stay with that image a little longer, because the cooling happening deep within our planet turns out to influence far more than just volcanic activity and plate tectonics. It reaches into nearly every corner of Earth's long-term geological story. As Earth's interior continues to lose heat, gradually, over billions of years, the effects ripple outward in ways that touch the entire structure of the planet. Mountain building slows. The recycling of ocean crust through subduction zones weakens. Earthquakes, which occur because of the friction and movement between shifting tectonic plates, become less frequent, and eventually, less intense. The entire dynamic, restless character of Earth's surface, the very quality that has continuously reshaped continents, opened and closed ocean basins, and lifted entire mountain ranges skyward over hundreds of millions of years, begins to settle into stillness. It's worth appreciating just how much of what we consider permanent about this planet actually depends on that ongoing internal heat. The Himalayas, still slowly rising today as the Indian subcontinent continues pressing northward into Asia. The Pacific Ring of Fire, alive with volcanic activity because of ongoing plate movement beneath the ocean floor. Even the shape of the continents themselves, drifting and rearranging across hundreds of millions of years, in that great, slow dance geologists call continental drift. All of it, ultimately, powered by heat rising up from Earth's core. And all of it, eventually, destined to quiet down, as that internal fire continues its long, gradual dimming. So even setting aside the question of whether Earth is ever physically engulfed by the Sun, a question we'll return to shortly, the planet's fate is already being written by forces entirely independent of that dramatic possibility. The slow brightening of the Sun above. The slow cooling of Earth's molten heart below. Two processes, operating on their own separate timescales, each contributing its own chapter to this unfolding story, regardless of how the Sun's final act eventually plays out. This is really the heart of what we've been exploring together across this entire journey so far tonight. Earth's long-term fate isn't a single thread, dependent on just one variable. It's a story woven from multiple, interconnected strands, the Sun's steadily increasing brightness, yes, but also the particular chemistry of Earth's surface rock, the pace at which carbon dioxide gets drawn out of the atmosphere through weathering, and the deep, patient cooling of the planet's interior, quietly determining how long active geology continues at all. Remove any one of these threads, and the whole story would unfold differently. Together, they weave something far more intricate than a simple countdown to a single dramatic ending. There's yet another thread woven into this story, one that has nothing to do with heat or chemistry at all, the quiet, ongoing influence of gravity, reaching out from other objects across the solar system. Earth doesn't exist in isolation. It orbits the Sun alongside 7 other planets, countless moons, asteroids, comets, and vast populations of smaller bodies, all of them locked together in an intricate, ongoing gravitational relationship. And over sufficiently long timescales, these gravitational interactions can subtly, gradually influence Earth's own orbital path. Most of the time, these effects are small, almost negligible, across any time frame we'd normally think about. The gravitational pull of Jupiter, for instance, the largest planet in our solar system, exerts a constant, steady influence on the orbits of everything around it, including Earth. Over the course of a single human lifetime, this influence is utterly imperceptible. But mathematics doesn't only work over human lifetimes. Given enough time, measured not in centuries but in hundreds of millions, even billions of years, these small gravitational nudges can accumulate into meaningful, measurable changes. Scientists sometimes describe this using the term orbital resonance, a phenomenon where the gravitational influence of one body, repeated in a regular, rhythmic pattern over enormous stretches of time, gradually reshapes the orbit of another. It's a bit like pushing a child on a swing. Any single push barely changes anything at all. But repeated, rhythmic pushes, timed just right, can gradually build up into a much larger swing than any single push could ever produce on its own. Applied to planetary orbits across billions of years, this same principle means that Earth's path around the Sun isn't necessarily fixed and unchanging, the way it might appear across the comparatively brief span of recorded human history. Over sufficiently vast timescales, it's possible for Earth's orbit to shift, subtly, in response to the ongoing gravitational influence of its planetary neighbors. This possibility adds yet another layer of complexity to Earth's long-term story, and it's worth spending a moment with, because it changes the fundamental shape of the question we're asking. It's not simply, how will Earth's surface change as the sun brightens? It's also, will Earth's orbital position itself remain stable across these same vast stretches of time? And that turns out to be a genuinely open, actively researched question, one where gravitational interactions with other solar system objects could meaningfully alter Earth's long-term path in ways that are difficult to predict with total precision, this many billions of years in advance. These kinds of gravitational influences can work in more than one direction, too. In certain scenarios modeled by researchers, gravitational interactions with other planets, particularly the larger, more influential bodies like Jupiter and Saturn, could very gradually nudge Earth's orbit outward, farther from the Sun, over sufficiently long timescales. In other scenarios, the interactions could push in the opposite direction, or produce more complex, less predictable shifts in the shape of Earth's orbit, rather than simply moving it inward or outward in a straightforward way. It's genuinely difficult to overstate just how sensitive these kinds of long-term gravitational calculations can be. Even tiny differences in our current measurements of planetary positions and masses, differences far too small to matter for any near-term prediction, can compound dramatically when projected forward across hundreds of millions or billions of years. This is part of what makes modeling Earth's gravitational future, alongside its atmospheric and geological future, such a genuinely challenging and fascinating area of ongoing scientific research. Given everything we've explored so far tonight, the atmospheric changes, the shifting oceans, the cooling interior, and now these subtle gravitational influences from across the solar system, it's worth pausing to reflect on something important about how scientists actually approach a story this vast and this distant. They don't claim to know, with total, unwavering certainty, exactly what will happen to Earth, down to the precise year, a billion or more years from now. Instead, scientists treat the far future the way any careful, honest researcher treats a genuinely complex question, as a landscape of probabilities, rather than a single, fixed, predetermined outcome. This might initially sound like uncertainty in a discouraging sense, as though scientists simply don't know enough to give us a clear answer. But that's not quite right. It reflects something more like intellectual honesty and genuine scientific care. When you're modeling a system as complex as an entire planet, interacting with an entire star, across a timescale of billions of years, there are naturally many variables at play: atmospheric chemistry, geological activity, orbital mechanics, solar physics, each carrying its own margin of uncertainty. Rather than pretending to a false precision that the science simply doesn't support, researchers instead describe a range of plausible outcomes, each one grounded in careful modeling, each one representing a genuinely possible path Earth's story could take. This is, in many ways, simply how good science works, at any time scale. Think about it in terms you might already be familiar with. In the world of near-term weather prediction, meteorologists commonly describe outcomes in terms of probability, a 70% chance of rain, for instance, rather than a flat, certain declaration that it either will or won't rain tomorrow. That probabilistic framing isn't a weakness in the forecast. It's an honest reflection of a genuinely complex, difficult to predict system. Now extend that same kind of thinking outward, from a single day's weather to the next several billion years of an entire planet's story. Naturally, the uncertainty grows. But the underlying scientific approach remains exactly the same. Researchers gather the best available data, build careful models grounded in physics and chemistry and geology, and then describe a range of plausible outcomes, each with its own degree of scientific support, rather than committing to any single, falsely precise narrative. This is precisely why, throughout tonight's exploration, you've heard multiple, sometimes differing estimates for many of these events: 1.3 billion years for the loss of complex life in one model, 1 billion years in another, 1.5 billion years in yet another. These aren't contradictions to be resolved by picking a winner. They're honest reflections of a genuinely complex, evolving field of research, each estimate representing a careful, well-reasoned possibility, each one helping to narrow down, a little further, our collective understanding of where Earth's long story is ultimately heading. Scientists think of the far future, then, not as a fixed, unchangeable script, written in advance and simply waiting to be discovered, but as a genuine range of possibilities, shaped by processes we can measure and model today, but never predict with absolute, perfect certainty. It's a subtle but important shift in perspective, and one worth carrying with us as we continue moving forward, into the more distant reaches of this story. And now, we arrive at a point in Earth's future where nearly all of these different models, despite their varying assumptions and differing estimates, begin to agree far more closely with one another. A point that has, for generations, captured the imagination of scientists and storytellers alike. Around 5 billion years from now, the Sun is expected to enter the most dramatic phase of its own life story, becoming what astronomers call a red giant. At that point, having exhausted the hydrogen fuel at its core, the Sun will begin fusing hydrogen in a shell surrounding that core instead, a process that causes the outer layers of the star to expand dramatically outward, while simultaneously cooling in temperature, shifting from the familiar yellow-white light we see today toward a deep, glowing red. The Sun, in other words, will grow enormously larger, and in a very real sense, enter the final, most transformative chapter of its own long stellar life. This is the moment so many people picture when they first imagine the Sun's eventual fate, and Earth's fate along with it. And it's a moment we'll spend real time exploring together, in the chapters still ahead. For now, though, let this settle quietly. We've journeyed through the slow cooling of Earth's molten heart, through the patient, invisible tug of gravity reaching across the solar system, and through the careful, honest uncertainty that scientists bring to a story this vast. We arrive now at the threshold of the Sun's own transformation, 5 billion years away, a distance so vast it can hardly be held in the mind at all. And yet, somehow, entirely real, entirely part of the same continuous story we've been tracing together, one patient, quiet fact at a time. Let's carry this thread forward, gently, into what comes next. We stand now at the edge of that threshold we mentioned a moment ago, 5 billion years into the future, at the beginning of the most transformative chapter in the sun's entire life. To understand what happens next, it helps to step back briefly and think about what a star actually is, at its core, quite literally. For the vast majority of its life, a star like our Sun exists in a kind of extraordinary, sustained equilibrium. Deep within its core, immense pressure and temperature fuse hydrogen atoms together, forming helium, and releasing enormous amounts of energy in the process. This energy pushes outward, in the form of light and heat, constantly working against the star's own gravity, which is just as constantly pulling everything inward. For billions of years, these two forces, the outward push of fusion and the inward pull of gravity, remain in a remarkably stable balance. This is what astronomers call the main sequence, the long, steady, middle chapter of a star's life. Our Sun has been living through this chapter for about 4.5 billion years already, and is expected to continue for perhaps 5 billion more. But that balance cannot last forever. A star's core only contains so much hydrogen. And eventually, inevitably, no matter how patiently that fuel gets consumed, it runs out. This is the moment that marks the true turning point in a star's life, the boundary between its long, stable middle age, and the more dramatic, transformative chapter that follows. When the Sun eventually exhausts the hydrogen fuel at its core, it doesn't simply go dark or fade away quietly. Instead, it begins an entirely new phase of stellar evolution, one governed by a different internal process altogether. Without hydrogen fusion happening at the core any longer, the delicate balance that has defined the Sun's entire life so far begins to shift. Gravity, no longer held perfectly in check by the outward pressure of core fusion, begins pulling the core inward, causing it to contract and heat up even further. And this, counterintuitively, is precisely what sets the stage for the Sun's outer layers to do something rather dramatic, expand outward, dramatically, into what we call the red giant phase. This marks the formal beginning of that red giant transformation we touched on briefly before. It's the direct, inevitable consequence of the Sun running out of the one fuel source that has powered its stable, steady light for its entire life up to this point. Once that fuel is gone, everything about the star begins to change, not randomly, but according to a well-understood sequence of physical processes that astronomers have studied extensively, both through detailed stellar models, and by observing countless other stars throughout the universe currently living through this exact same transition. It's worth pausing here to notice something almost poetic in the physics of this process. The Sun's coming expansion, this vast, dramatic swelling that will eventually transform it from a modest, stable, yellow-white star into an enormous, glowing red giant, doesn't happen because the Sun is gaining energy, or somehow becoming more powerful. It happens, paradoxically, because the core is running out of fuel and beginning to collapse inward. In stellar physics, this pattern repeats again and again. The outer expansion of a star is often the direct result of contraction and heating happening deep within its core. Vastness, in other words, emerging quietly from collapse. So what exactly triggers this dramatic expansion? Once the Sun's future core hydrogen supply is finally exhausted, the answer lies in a delicate shift of where fusion actually takes place within the star. Once the hydrogen in the very center of the Sun's core has been fully converted into helium, fusion can no longer continue there, at least not initially, because the temperatures required for helium fusion are considerably higher than what's needed for hydrogen fusion. But just outside that now inert helium core, there remains a thin shell of hydrogen that hasn't yet been consumed. And it's within this surrounding shell that fusion continues, shifting from the core itself outward into this thinner, surrounding layer. This shift, from core fusion to shell fusion, turns out to be the key mechanism driving the Sun's future expansion. Shell hydrogen fusion actually produces even more energy than the earlier core fusion did, and this surge of energy pushes outward against the Sun's outer layers with tremendous force, causing them to expand dramatically, swelling the star to many times its current size. Meanwhile, deep within, the helium core itself, no longer producing energy through fusion, continues contracting under the relentless pull of gravity, growing steadily hotter and denser as it does. This creates a genuinely striking internal structure, one that might seem almost contradictory at first, until you understand the physics behind it. As the Sun's core shrinks and heats up, its outer layers simultaneously expand and cool. The star, in other words, becomes larger and dimmer in surface temperature at exactly the same time that its interior becomes smaller and hotter. It's a strange, beautiful kind of stellar inversion, contraction and expansion happening simultaneously, in different layers of the very same star. And this expanding outer envelope is precisely what gives red giant stars their distinctive, glowing red-orange color. As the outer layers expand outward, spreading the star's total energy output across a vastly larger surface area, that surface cools considerably, shifting the light it emits away from the bright yellow-white we're familiar with today, toward the deeper, softer red and orange tones that give red giant stars their name, and their strange, dramatic beauty in the night sky. Eventually, as this contraction of the core continues, the temperature and pressure deep within finally become extreme enough to ignite an entirely new kind of fusion, one involving helium itself. During this transition, once the hydrogen fuel at the very center is truly gone, the Sun will begin burning helium, fusing it into heavier elements like carbon and oxygen, in a process that requires temperatures far higher than the hydrogen fusion that powered the Sun for the majority of its life. This moment, the ignition of helium fusion, actually happens in a rather sudden, dramatic burst, at least on stellar timescales, an event astronomers call the helium flash. For a brief period, astronomically speaking, the core's energy output spikes tremendously, before the star settles into a new, if temporary, kind of equilibrium, now powered by helium fusion rather than hydrogen. It represents yet another chapter within this larger chapter, a further transformation nested inside the broader arc of the Sun's red giant evolution. Now, all of this internal transformation, this shift from core to shell fusion, this expansion of the outer layers, has enormous consequences for anything, or anyone, orbiting the Sun. And chief among these consequences is a fundamental shift in what astronomers call the habitable zone. The habitable zone, sometimes described more poetically as the Goldilocks zone, refers to the range of distances from a star where conditions are, in principle, just right for liquid water to exist stably on a planet's surface, not so close that water boils away entirely, and not so far that it freezes solid. It's the zone that has allowed Earth, sitting at just the right distance from our Sun to maintain liquid oceans, and by extension, life, across billions of years. But the habitable zone isn't a fixed, permanent location in space. It's defined entirely by the star's brightness and heat output, which means that as a star's luminosity changes, the habitable zone shifts along with it. And as we've discussed throughout tonight's journey, the Sun's luminosity has been slowly, steadily increasing across its entire lifetime, a gradual brightening that, as we explored earlier, is already expected to render Earth uninhabitable long before the Sun ever reaches this current, dramatic red giant stage. Now, as the Sun expands and transforms even further, that habitable zone will shift dramatically and rapidly outward, moving away from the Sun's growing heat, toward the cooler, more distant reaches of the solar system. This brings us to a genuinely poignant realization, one that quietly reframes so much of what we've explored together tonight. Earth is currently sitting comfortably within the Sun's habitable zone, occupying precisely the right distance to maintain the liquid oceans and stable climate that made complex life here possible in the first place. But that zone, as we've now seen, is not a permanent address. It is a temporary, shifting region, tied directly to the Sun's own evolving nature. And as the Sun brightens, and eventually swells into a red giant, that habitable zone will move steadily outward, leaving Earth's current position behind entirely, drifting instead toward the outer solar system, toward the distant, icy realms of Jupiter, Saturn, and beyond. It's worth sitting with that image for a moment. The very quality that makes Earth so remarkably suited to life, its particular distance from the Sun, was never a permanent, guaranteed feature of this planet's existence. It was always, in a sense, a fortunate, temporary alignment, a moment in time, however vast that moment might be by human standards, when a young, growing star happened to shine at just the right brightness to keep this one particular planet, at this one particular distance, comfortably livable. And like all temporary alignments, it is, in the long run, destined to shift, and eventually, to end. There's another important consequence of the Sun's red giant transformation, one that turns out to matter enormously for Earth's own physical fate, and it involves not just the Sun's light, but its very mass. As the Sun evolves into a red giant, its outer layers become increasingly loosely bound by gravity, extended and thinned out as they are stretched dramatically outward from the core. And this loosening allows the Sun to begin shedding enormous quantities of its own material, carried away steadily through what's known as the solar wind, a continuous outward stream of charged particles that every star, including our Sun today, sends flowing out into space. Right now, in the Sun's current, stable phase of life, this solar wind is relatively gentle, a steady but modest outflow of particles that has little meaningful effect on the Sun's overall mass, even across billions of years. But during the red giant phase, this solar wind intensifies dramatically, becoming far more powerful, as the Sun's outer layers, now far less tightly bound by gravity than they once were, become progressively easier to strip away and carry outward into space. Over the course of this transformation, models suggest the Sun will lose a truly substantial portion of its overall mass, roughly 30% of its total mass, carried away gradually through this intensified solar wind, over the course of the red giant phase. This is a genuinely enormous amount of material to lose, and it turns out to matter far beyond the sun's own internal story. Because a star's mass is precisely what determines the strength of its gravitational pull, and that gravitational pull is precisely what holds the entire solar system in its current configuration, including the orbits of every planet, Earth very much among them. As the sun sheds roughly a third of its total mass, its gravitational grip on the rest of the solar system correspondingly weakens. And weaker gravity means looser orbits, planets held less tightly in their current paths, free to drift gradually outward, into wider, more distant orbits than the ones they currently maintain. This detail turns out to be enormously significant for a question we've been circling around throughout tonight's exploration, a question we'll finally turn to directly in the chapter ahead. Because if Earth's orbit itself begins shifting outward, in response to the sun's diminishing mass, at precisely the same time that the sun itself is expanding dramatically outward, growing larger and larger as it evolves into a red giant, then Earth's ultimate fate may hinge on a genuinely delicate, uncertain race between these two competing movements. The sun growing larger, reaching outward, and Earth, potentially, drifting outward as well, in response to that same star's diminishing hold. Whether Earth ultimately escapes that expanding reach, or whether it's eventually caught within it, is a question that scientists have modeled carefully, from multiple angles, arriving at conclusions that are genuinely fascinating, and in their own quiet way, remarkably suspenseful, even across a timescale as vast as this one. We'll turn to that very question next, tracing this delicate gravitational dance all the way to its conclusion. For now, let this settle gently, the sun, slowly shedding its own substance into the surrounding dark, its gravity loosening its hold on everything that orbits it, while somewhere nearby, a small, rocky planet drifts quietly in the balance, caught between an expanding star and a gravity that no longer pulls quite as tightly as it once did. We left that image hanging in the balance, a small, rocky planet drifting quietly, caught between an expanding star and a loosening grip of gravity. Let's follow that delicate tension all the way through now, because it turns out to be one of the more genuinely suspenseful questions in this entire long story, one that scientists have modeled with real care and real nuance. As we discussed a moment ago, the sun's substantial mass loss during its red giant phase, that roughly 30% of its total mass, carried away steadily through an intensifying solar wind, has a direct and measurable effect on the orbits of everything around it. With less mass, the sun's gravitational pull weakens correspondingly, and planets held in that gravitational grip naturally respond by settling into wider, more distant orbits. For Earth specifically, models suggest this effect could be substantial. If mass loss were the only force at work, with nothing else complicating the picture, Earth's orbit could drift outward to somewhere around 1.7 astronomical units, nearly twice its current distance from the Sun. To put that in perspective, 1 astronomical unit is simply the average distance between Earth and the Sun as it stands today, the very distance that currently keeps our planet so comfortably positioned within the habitable zone. A shift out to 1.7 astronomical units would place Earth's orbit roughly in the neighborhood where the asteroid belt currently sits, a genuinely significant relocation, achieved gradually, over the course of the Sun's red giant transformation. This possibility, that Earth's own orbit might drift outward in direct response to the Sun's diminishing mass, offers a genuinely hopeful thread within this otherwise sobering story. Some researchers have proposed that this outward drift could be enough, on its own, to help Earth avoid the most dramatic and final fate awaiting the inner planets, outright engulfment by the Sun's expanding outer layers. If Earth's orbit widens quickly enough, and significantly enough, it's possible the planet could stay just ahead of the Sun's growing reach, always drifting a little farther outward, precisely as the star itself grows a little larger, maintaining just enough distance to avoid being swallowed entirely. But this hopeful possibility comes with an important complication, one that keeps this entire question genuinely uncertain, right up to the present moment in scientific research. Because the widening of Earth's orbit is only one half of the story. There's a second, competing force at work as well, one that pulls in precisely the opposite direction. That second force is something astronomers call tidal drag, and it works quite differently from the simple, straightforward effect of the Sun's mass loss. As the Sun's outer layers expand outward, drawing closer and closer to Earth's orbit, they begin exerting a subtle gravitational pull on Earth itself, a tidal force, not unlike the way Earth's own gravity currently pulls at the Moon, gradually influencing its orbit over time. This tidal interaction between Earth and the Sun's swelling outer atmosphere tends to work against Earth's outward drift, creating a kind of gravitational drag that pulls Earth's orbit inward, back toward the Sun, even as the mass loss effect is simultaneously working to push it outward. So Earth's ultimate fate, whether it manages to drift safely outward, or whether it ultimately spirals inward toward the Sun's expanding reach, comes down to a genuine, delicately balanced competition between these two opposing forces. The outward push from the Sun's diminishing mass, on one side. The inward pull of tidal drag from the Sun's expanding, encroaching outer layers, on the other. Two forces, working in direct opposition, with Earth's entire future caught somewhere in the balance between them. Scientists describe this quite directly as a genuine tug-of-war, and it's a wonderfully apt way to think about it. Picture two teams, pulling on opposite ends of the same rope, each with real strength behind them, neither one able to immediately overpower the other. Earth's orbital fate hangs somewhere along that rope, waiting to see which side ultimately gains the advantage, as the Sun continues its long, dramatic transformation. For a long time, this question remained genuinely unresolved in the scientific literature, with different research teams, using different assumptions and different models, arriving at meaningfully different conclusions. Some models suggested the outward push from mass loss would win out comfortably, allowing Earth to escape engulfment with room to spare. Others suggested the inward pull of tidal drag would ultimately dominate, dragging Earth inexorably closer to the Sun's expanding surface, regardless of how much the Sun's own mass diminished along the way. It's worth appreciating just how delicately balanced this particular calculation turns out to be. We're not talking about a contest with an obvious, foregone conclusion. We're talking about two genuinely comparable forces, each capable, under slightly different assumptions, of tipping the outcome one way or the other. This is precisely the kind of nuanced uncertainty that makes this particular chapter of Earth's story so genuinely compelling to follow, even now, even as researchers continue refining their models. Some more recent research has attempted to narrow this uncertainty down, by focusing specifically on the boundary between planets that survive this transformation and planets that don't. One notable estimate suggests that any planet currently orbiting within about 1.15 astronomical units of the Sun, a boundary that sits just slightly beyond Earth's current orbital distance, could ultimately face destruction, engulfed by the Sun's expanding outer layers, regardless of any outward drift caused by the Sun's mass loss. This figure matters enormously, because Earth's current orbital distance sits at exactly 1 astronomical unit, by definition. Which means Earth currently finds itself sitting frustratingly close to this particular danger threshold, near enough that even a modest miscalculation, or a slightly different set of assumptions about tidal drag or mass loss rates, could plausibly shift Earth from one side of that boundary to the other. And the scale of the Sun's eventual expansion only heightens the tension surrounding this particular calculation. Some models suggest the Sun could eventually grow to a radius of roughly 1 astronomical unit during its most extended phase as a red giant. Read that again, slowly, and let it settle. A radius of 1 astronomical unit means the Sun's outer surface would extend all the way out to Earth's current orbital distance. The Sun, in other words, could potentially grow large enough to physically reach the very orbit Earth occupies today, regardless of how far Earth's own orbit might have drifted outward by that point. This gives a real sense of just how extreme, and how close, this particular question actually is. We're not talking about a star that grows moderately larger, leaving a comfortable safety margin for the planets nearby. We're talking about a star potentially expanding enormously, reaching outward across a distance that currently takes sunlight over 8 minutes to travel, swelling to fill a significant portion of what we currently think of as the inner solar system entirely. Given an expansion of that scale, it's worth turning briefly to the 2 planets that orbit even closer to the Sun than Earth does, Mercury and Venus, because their fate, unlike Earth's, appears to be far less ambiguous. As the Sun expands during its red giant phase, growing larger in a slow, continuous progression, it's expected to engulf the innermost planets first, beginning with Mercury, the closest planet to the Sun, and then Venus shortly afterward. Mercury, orbiting at less than half of Earth's current distance from the Sun, offers essentially no realistic chance of escaping engulfment, regardless of how the competing forces of mass loss and tidal drag ultimately play out. Its orbit is simply too close, too deep within the danger zone, for any plausible outward drift to matter. Venus occupies a slightly more ambiguous position, given its greater distance from the Sun compared to Mercury, but even in the more optimistic scenarios modeled by researchers, scenarios where Earth manages to narrowly escape engulfment thanks to a favorable outcome in that gravitational tug-of-war we described, Venus is still expected to be swallowed by the Sun's expanding outer layers. Its orbital distance simply doesn't offer enough of a margin, even under the most favorable set of assumptions currently being considered. So somewhere within this story, even in the versions where Earth manages to survive, quite literally, by the narrowest of margins, its 2 planetary neighbors, Mercury and Venus, worlds that have shared this solar system with Earth since its very formation, over 4.5 billion years ago, are still expected to meet a far more definitive end, drawn directly into the Sun's expanding, engulfing reach. But even in the scenarios where Earth manages to avoid this same fate, where the outward drift from the sun's mass loss narrowly wins out over the inward pull of tidal drag, that survival, if we can even call it that, comes with an important and sobering caveat. Because avoiding outright engulfment doesn't necessarily mean avoiding catastrophic harm. Even if Earth's orbit remains just beyond the sun's expanding physical surface, the sheer proximity involved in this scenario means Earth could still find itself close enough to the swelling sun to lose its atmosphere entirely, stripped away by the immense heat and radiation pouring outward from a star that, even at its new, more distant configuration, remains dramatically closer and dramatically more intense than the sun we experience today. It's a genuinely sobering thought to sit with. Even in what researchers consider the more fortunate outcome, the version of this story where Earth technically survives, technically avoids being swallowed whole by an expanding star, the planet that emerges on the other side of that ordeal may bear little resemblance to the Earth we know today. No atmosphere to speak of. No protective layer to shield whatever, if anything, remains on the surface. A bare, scorched, technically still orbiting remnant, having narrowly escaped complete destruction, only to find itself stripped of nearly everything that ever made it a living, breathing world in the first place. We'll continue tracing this delicate, uncertain story forward, into what comes next, following Earth's narrow, uncertain path through this final stellar transformation, and asking what, if anything, might remain on the other side of it. For now, let this settle quietly, a small planet, caught in a tug-of-war between an expanding star and its own weakening gravity, its ultimate fate still balanced, delicately, on the finest of margins. Let's return now to that scorched, uncertain planet we left drifting at the edge of a swelling star, and look more closely at what its surface would actually experience in those final stretches of the sun's transformation. Long before the question of engulfment is even settled, one way or another, Earth's environment will already have changed beyond recognition. The sun's steadily increasing heat, intensifying dramatically as it moves deeper into its red giant phase, will make conditions on Earth's surface entirely incompatible with anything resembling the oceans, the climate, or the delicate atmospheric balance we know today. The blue oceans, the white clouds drifting overhead, the gentle blanket of nitrogen and oxygen that has sustained life for billions of years, none of it built to withstand a sun burning this much brighter, this much closer, than the one we know now. This is where the two possible outcomes we explored earlier begin to converge, in a strange sort of way, toward a similarly bleak destination. As we discussed, some models suggest Earth may end up transformed into something closely resembling Venus, a scorched world wrapped in a thick, hostile, crushing atmosphere. Other models suggest the opposite extreme, a planet stripped instead of any meaningful atmosphere at all, left bare and exposed beneath a swollen, intensely radiant sunday. Two very different pictures, in terms of atmospheric detail, and yet both arriving, by different paths, at the same fundamental conclusion: a world no longer capable of sustaining anything resembling the rich, complex life that once called it home. And this brings us back to that delicate tug-of-war we spent so much time exploring a moment ago, between the sun's mass loss pulling Earth's orbit gently outward, and the tidal drag from the sun's expanding atmosphere pulling it back in. Even in the scenarios where that contest resolves in Earth's favor, where the planet narrowly avoids being swallowed entirely by the sun's expanding outer layers, this doesn't represent anything close to a triumphant survival story. It's better described, in the careful language of the researchers who study it, as a devastated survival. Earth persists, technically, as a physical object still tracing an orbit around its star. But everything about it that once made it habitable, its atmosphere, its oceans, its climate, its capacity to sustain any form of complex life, would already be gone, long before this particular question was ever even settled. It's worth acknowledging, though, that this picture has genuinely been evolving within the scientific community, even in fairly recent years. Some of the newer research on this question, building on more refined models and more precise calculations, suggests a slightly more hopeful possibility than earlier studies once proposed. This newer body of work suggests Earth might genuinely survive the Sun's red giant phase as a physical, intact planet, continuing to orbit even after the Sun has completed its most dramatic transformation. It would still, without any real doubt, be far too hostile an environment to support life as we currently understand it. But the planet itself, as a physical body, orbiting where it has always orbited, or somewhere reasonably close to it, may actually persist, rather than being consumed entirely by an expanding, engulfing star. This shift in scientific thinking traces back, in part, to a deeper re-examination of exactly how strong that tidal drag effect actually is. Remember, tidal drag was the force pulling in the opposite direction from the Sun's mass loss, tugging Earth's orbit inward, back toward the encroaching star, even as the weakening solar gravity pulled it outward. For a long time, many models treated this tidal effect as a particularly powerful, dominant force, strong enough, in many earlier calculations, to overcome the outward push from mass loss entirely, dragging Earth inevitably toward engulfment regardless of how much the Sun's own mass diminished along the way. But newer, more refined models suggest that some of these earlier calculations may have overestimated just how strong that tidal pull really is. With more careful accounting of the physics involved, the drag between Earth and the Sun's expanding, increasingly diffuse outer atmosphere appears somewhat weaker than previously assumed, tipping the balance of that long-standing tug-of-war a bit more favorably toward Earth's survival. It's a good example of how science genuinely refines itself over time, not through sudden, dramatic reversals, but through careful, incremental improvements in modeling and calculation, each new study adding a bit more precision to a question that has occupied researchers for decades. Even with this revised, somewhat more optimistic understanding of tidal drag, though, the danger hasn't disappeared entirely. It's simply been recalculated, rather than eliminated. Tidal interactions between Earth and the Sun's swelling outer layers could still, under the right conditions, drag Earth inward, into the Sun's expanding atmosphere, even in scenarios where the planet would have otherwise remained safely beyond the Sun's physical surface, based on the mass loss effect alone. This remains a genuinely live possibility within the current research, a reminder that even revised, more careful models still leave meaningful uncertainty in exactly how this particular chapter concludes. There's an interesting extension to this story, one that broadens our view a bit beyond Earth alone. Because if the newer, more optimistic calculations regarding tidal drag turn out to be accurate, they don't just improve Earth's prospects specifically, they also affect how researchers think about Mars. Mars orbits considerably farther from the Sun than Earth does, at roughly 1.5 times Earth's current distance. And under these newer models, researchers now think Mars, too, may survive the Sun's red giant phase, under broadly similar conditions to those now being considered for Earth. Mars's greater distance offers it a somewhat larger margin of safety to begin with, and if the revised tidal drag calculations hold up under further scrutiny, that margin may be enough to carry Mars through this entire transformation relatively intact, at least as a surviving physical body, even as its own already thin atmosphere presumably faces its own additional challenges from a dramatically brightened, swollen sun. There is something quietly fascinating in imagining these two neighboring worlds, Earth and Mars, potentially emerging together on the other side of the Sun's most dramatic transformation, two scorched, lifeless companions, drifting through a solar system that would look almost unrecognizable compared to the one we know today, yet still, in some reduced, transformed sense, continuing their long orbital journey around the same star that has always anchored them both. Given how genuinely difficult it is to model these processes with total precision, purely through calculation and theory, astronomers have also turned to a rather different, and remarkably useful, source of insight, observing other stars, elsewhere in the galaxy, that happen to already be living through the very transformation our own Sun has not yet begun. One particularly valuable example is a red giant star known as L2 Puppis, located a few hundred light-years from Earth. This star has captured considerable scientific attention, precisely because it offers something rare and valuable, a kind of preview, observed directly through telescopes, of what our own Sun's future might genuinely look like, rather than relying purely on theoretical modeling. L2 Puppis is believed to be a star quite similar in its original mass and composition to our own Sun, only considerably further along in its stellar life, having already progressed well into its own red giant transformation. By studying this star directly, its size, its temperature, its behavior, astronomers gain a genuine, empirical window into the kind of transformation the Sun itself will eventually undergo, offering a valuable check against the purely theoretical models we've been discussing throughout tonight's story. And what makes L2 Puppis particularly useful for exactly this purpose is something orbiting alongside it. This star has a companion object, in orbit around it at a distance that, remarkably, falls within a comparable range to Earth's current distance from our own Sunday. This detail transforms L2 Puppis from simply being an interesting example of stellar evolution, into something considerably more specific and valuable, a genuine natural laboratory, allowing astronomers to observe, directly, how an orbiting companion behaves and survives, or fails to survive, in close proximity to a star undergoing precisely this kind of dramatic red giant transformation. In effect, astronomers have identified, out there among the countless stars scattered across our galaxy, something like a distant twin of our own Sun-Earth system, caught at a much later stage in its evolution than our own. It's a rare and genuinely valuable opportunity, the chance to observe, with real telescopes, pointed at a real star hundreds of light years away, a glimpse of the very future our own solar system is slowly, patiently moving toward. There is something quietly moving about this particular kind of scientific work. Long before our own Sun ever begins its own transformation, 5 billion years from now, astronomers today can look outward, into the depths of the galaxy, and find other stars, other systems, already living through chapters that our own solar system has not yet reached. It's a bit like reading ahead in a book that hasn't fully arrived yet in front of you, borrowing pages from a neighboring story, written in the same language of physics and starlight, to understand a little more clearly what still lies ahead in our own. We'll continue following this thread forward, gently, into the chapters still ahead of us tonight, carrying with us this new perspective, borrowed from distant stars like L2 Puppis, as we return once more to our own sun, and to the final, most dramatic stretches of its own long, transformative story. For now, let this settle quietly, a distant star, hundreds of light years away, quietly living out a version of our own future, its faint light traveling all this way, across centuries, simply to help us understand, a little more clearly, what waits for us, patiently, so very far ahead. That distant glimpse of L2 Puppis, and the companion quietly orbiting it, offers something more than just scientific curiosity. It gives astronomers a genuine, real-world reference point, a system that lets them compare their theoretical models against something actually observed, actually measured, actually happening right now, out there in the depths of the galaxy. Rather than relying purely on equations and simulations, they can look at this distant system and ask, does what we're seeing here match what our models predict for our own future? It's a rare kind of scientific privilege, having a working example to check your homework against, even when that example happens to sit hundreds of light years away. And L2 Puppis isn't entirely alone in offering this kind of insight. Astronomers have continued searching the galaxy for other systems that might serve a similar purpose, and they've identified additional examples, other distant planetary systems that appear to resemble what our own Sun and Earth might look like, billions of years from now, once this same red giant transformation has run its course. Each of these distant systems adds another data point, another piece of evidence, helping researchers refine and cross-check their understanding of exactly how stars like our Sun behave as they age, and exactly what happens to the planets that continue orbiting them through that transformation. This growing body of real, observed examples matters quite a bit, because it helps move this entire conversation beyond pure theory. It's one thing to build a mathematical model of how a star's mass loss and tidal drag might interact, over billions of years. It's another thing entirely to point a telescope at an actual star, actually living through that exact process, and see how closely reality lines up with those calculations. Each distant twin system discovered adds a little more confidence, or occasionally, a little more necessary revision, to the models scientists use to describe our own Sun's future, and Earth's fate along with it. Taken together, this combination of careful theoretical modeling and direct astronomical observation brings us to where the science currently stands, and it's worth stating this clearly, because it's easy to conflate two ideas that are actually quite different from one another. Scientists still consider Earth's exact fate, in terms of whether it survives the Sun's red giant phase as an intact orbiting body or not, to be a genuinely unresolved question, one where research continues to refine and adjust the answer. But it's essential to understand that survival, in this narrow, technical sense, and habitability, in the broader sense we've been exploring throughout this entire journey, are two very different outcomes. This distinction matters enormously, and it's worth sitting with for a moment. A planet can technically survive, can continue circling its star, tracing more or less the same orbital path it always has, without that survival meaning anything at all in terms of that planet actually remaining a livable, hospitable world. Survival, in the strictest astronomical sense, simply means the planet is not physically consumed by the expanding star. It says nothing whatsoever about oceans, atmosphere, temperature, or anything resembling the conditions life would actually require. And so, even in the more optimistic scenarios we've explored tonight, the versions where Earth manages to avoid outright engulfment thanks to a favorable balance in that long tug-of-war between mass loss and tidal drag, a surviving Earth would not, in any meaningful sense, remain habitable. It would still be, by every meaningful measure, a scorched, airless world, its oceans long since evaporated and lost to space, its atmosphere stripped away by the sheer intensity of a nearby, swollen sun, its surface baked by heat far beyond anything any form of terrestrial life could ever tolerate. There's a particularly striking possibility that emerges from some of these models, one that carries its own quiet, haunting beauty. If Earth does survive the red giant phase, continuing to orbit even after the Sun completes this most dramatic chapter of its transformation, it may eventually find itself circling not the bright, familiar Sun we know today, but something considerably quieter and stranger. Because after a star like our Sun finishes its red giant phase, having fused the last of its available fuel, it typically sheds its remaining outer layers entirely, leaving behind only its small, dense, slowly cooling core, an object astronomers call a white dwarf. So in this particular version of Earth's far future, the planet, if it survives at all, may end up as a frozen, airless rock, still faithfully tracing its orbit, but now circling a small, dim, gradually fading stellar remnant, rather than the bright, warm, life-giving star it has always known. A white dwarf produces only a faint, residual glow, a fraction of the light and heat the Sun provides today, slowly cooling further over trillions of years to come. Earth, in this scenario, would drift through an increasingly cold, increasingly dark stretch of its orbit, illuminated by little more than a dim ember where its sun once blazed. It's a genuinely poignant image to hold in mind, this same planet that has spent billions of years bathed in warm, life-giving sunlight, nurturing oceans and forests and every living thing that has ever called it home, eventually reduced to a frozen, silent rock, circling the faint, fading remnant of the very star that once made all of that abundance possible in the first place. Of course, as we discussed a moment ago, there remains another plausible path entirely, one that doesn't end in ice and darkness, but in heat and desiccation instead. By this point in the story, Earth could just as easily resemble Venus, dry, blisteringly hot, wrapped in a thick, hostile atmosphere, or stripped bare of one altogether. Two very different pictures, frozen darkness under a dying star, or scorched, airless heat beneath an already departed one, and yet, remarkably, both remain genuinely live possibilities within current scientific modeling, depending on the precise details of Earth's orbital fate, and how the balance of forces we've discussed tonight ultimately resolves itself. Long before we even reach that final, distant chapter, though, involving white dwarfs and frozen orbits, there's an earlier, somewhat more immediate marker worth pausing on. Around 4 billion years from now, well before the sun even begins its red giant transformation in earnest. Models suggest Earth may already be completely barren. Not merely inhospitable to complex animal and plant life, as we explored earlier in tonight's journey, but barren in the fullest, most complete sense of that word. No plants, no animals, and crucially, no microbes either. This last detail matters quite a bit, and it's worth pausing on directly, because throughout most of this story, we've focused primarily on the loss of complex, visible life, plants, animals, the rich, layered biosphere that currently blankets Earth's surface. But microbial life is a different matter entirely. Microorganisms are famously resilient, capable of surviving in conditions that would be immediately lethal to any plant or animal, thriving in boiling hydrothermal vents, in deeply frozen ice, in highly acidic or highly saline environments that no more complex organism could ever tolerate. Microbial life has persisted through nearly every mass extinction event in Earth's entire history, quietly enduring conditions that wiped out almost everything else. So the suggestion that even microbial life may be entirely gone by around 4 billion years from now represents something genuinely significant, a marker of just how thoroughly hostile Earth's environment will have become by that point. It's not simply that the visible, familiar forms of life we know today will have vanished. It's that the very deepest, most resilient roots of life on this planet, the hardy, adaptable microorganisms that have outlasted asteroid impacts, ice ages, and volcanic catastrophes throughout Earth's entire 4.5 billion year history, will finally, at long last, have nowhere left to survive either. By this point in Earth's story, then, the long era of terrestrial life, stretching back nearly 4 billion years, to the very first simple organisms that emerged in ancient oceans, will have come to its quiet, final close. Earth will no longer be a habitable planet, in any sense of that word, for any form of life whatsoever. Not the complex, visible ecosystems that flourish today. Not even the humble, resilient microbial life that has persisted, quietly and continuously, since almost the very beginning of this planet's story. There's a natural question that arises from everything we've traced together so far tonight, one that shifts our attention, briefly, away from the planet itself, and toward any civilization that might still exist upon it, whether human, or something descended from us, reshaped by the vast stretches of time we've been discussing. Because if Earth's habitability genuinely comes to an end somewhere in that 1 to 1.5 billion year range we discussed earlier, long before the sun ever begins its dramatic red giant transformation 5 billion years from now, then any future civilization hoping to endure would need to relocate, to find a new home elsewhere, long before the sun's most destructive phase ever actually arrives. This is a genuinely striking way to reframe this entire, sweeping story. The sun's red giant phase, with all its dramatic imagery of an expanding, engulfing star, has always captured the popular imagination as the defining endpoint of Earth's future. But as we've traced together across tonight's journey, the true deadline, the point at which Earth actually stops being able to sustain life, arrives billions of years earlier than that dramatic finale. Any civilization hoping to witness, and survive, the sun's ultimate transformation would need to have already left this planet behind, long before that final chapter ever begins, carrying with them, out into the wider galaxy, whatever remains of the story that began here, on this quiet, blue world, so very long ago. We'll carry this thread forward gently, into the final stretches of tonight's exploration, following Earth's story all the way to its furthest, most distant horizon. For now, let this settle quietly, a planet falling silent, first of forests, then of creatures, then finally, of even its smallest, most resilient forms of life, drifting onward through the dark, patiently, toward whatever quiet fate finally awaits it. We ended a moment ago with the image of a planet falling quietly silent, drifting on toward whatever fate finally awaits it. And that image naturally raises a deeper question, one that sits just beneath the surface of everything we've explored so far tonight. What about us? What about whatever comes after us, however far removed, however transformed by the passage of time? Because woven into this entire scientific story are several genuinely open questions, questions that current research simply cannot yet answer with any real certainty, and it's worth spending some time with them directly, rather than passing over them too quickly. The first of these unresolved questions is deceptively simple to state, and yet almost impossible to answer with any real confidence. Will humans, or whatever humanity eventually becomes, still exist by the time the sun reaches its red giant phase, 5 billion years from now? It's worth pausing to appreciate just how vast a stretch of time that actually represents, from a human perspective. Modern humans, in our current biological form, have existed for perhaps 300,000 years. Civilization, in any recognizable sense, agriculture, writing, cities, has existed for roughly 10,000 years. 5 billion years is not simply a longer version of that timeline. It's a timeline so vast that our entire recorded history so far represents only the faintest, most infinitesimal sliver of it, a fraction of a percent of the time remaining before the sun even begins this transformation. Within a span that immense, almost anything becomes possible, and almost nothing becomes certain. Species evolve, or go extinct. Civilizations rise, fall, and are sometimes replaced by entirely different forms of intelligence altogether. Even the very concept of what counts as human, biologically, culturally, technologically, could shift so dramatically across billions of years that our current understanding of that word might barely apply at all, to whatever, or whoever, might still be around by that point. This isn't a question science can currently answer, because it depends not just on physics and geology, but on the far more unpredictable currents of evolution, technology, and history itself, unfolding across a scale of time we've genuinely never had to consider before. The second open question follows naturally from everything we've explored across tonight's journey, and it's one we've circled around quite extensively already. Does Earth itself, as a physical planet, actually survive the sun's red giant phase? We've spent considerable time tonight tracing the delicate tug-of-war behind this particular question, the competing forces of the sun's mass loss pulling Earth's orbit gently outward, and tidal drag from the sun's expanding outer layers pulling it back inward. We've discussed how newer research suggests this balance may tip somewhat more favorably toward Earth's survival than older models once assumed, and yet, even with these refinements, genuine uncertainty remains. This is not a settled question, not yet, and it may not be fully settled for a long time to come, as researchers continue refining their models and continue searching for additional distant systems, like L2 Puppis, that might offer further real-world evidence to test those models against. It's a strange thing to consider, that even the most basic question we might ask, does this planet, our planet, physically endure, remains genuinely open, dependent on calculations so delicately balanced that relatively small adjustments in our understanding of stellar physics can shift the answer meaningfully, one direction or the other. The third open question takes us somewhere considerably more abstract, moving beyond the fate of any single planet, or any single star, into questions about the fundamental nature of matter itself, across timescales that dwarf even the ones we've been discussing throughout tonight's journey. This question concerns something called proton decay, a theoretical process, predicted by certain models in particle physics, in which protons, one of the fundamental building blocks of all matter, might eventually break down into smaller particles, over timescales so vast they make even the Sun's 5 billion-year countdown look almost immediate by comparison. If proton decay does occur, and this remains a genuinely open question within physics, with ongoing experiments designed specifically to detect it, or rule it out, it would suggest that matter itself, the very stuff that makes up planets, stars, and everything else in the universe, is not permanent. Given a long enough stretch of time, unimaginably long, far beyond even the timescales we've explored across this entire story tonight, all ordinary matter might eventually decay away entirely, leaving behind nothing but a thin, diffuse residue of light and subatomic particles, drifting through an otherwise empty universe. It's worth being clear about the scale we're discussing here. If proton decay happens at all, current theoretical estimates suggest it would occur on timescales of at least 10 to the power of 34 years, and some estimates run considerably longer still. That's a 1, followed by 34 zeros. A number so large that comparing it to the age of the universe itself, a mere 13.8 billion years, is almost meaningless, the way comparing a single second to the entire history of human civilization would be meaningless. And yet, within the very long view of cosmology, this remains a genuinely serious question, one that touches on whether the universe itself has any kind of ultimate, final permanence, or whether, given enough time, absolutely everything eventually comes undone. Taken together, these three open questions, whether humanity persists, whether Earth itself survives, and whether matter itself is ultimately permanent, help frame something important about how we should think about this entire story we've been tracing together tonight. The far future isn't simply a fixed, predetermined sequence of events, waiting patiently to unfold exactly as calculated. It's better understood as a genuine intersection of several different kinds of knowledge, and several different kinds of uncertainty, layered together. Cosmic evolution, the slow, steady brightening of stars, the eventual transformation of the sun into a red giant, and someday, a white dwarf. Planetary physics, the intricate dance of orbital mechanics, tidal forces, and atmospheric chemistry that determines exactly what happens to a world like Earth, caught in the gravitational orbit of a changing star. And genuinely unanswered scientific questions, mysteries that current research simply hasn't resolved yet, questions that may take generations, or far longer, for scientists to eventually settle. This layered complexity is really the deeper theme running beneath everything we've explored across this entire journey tonight. Earth's long-term future isn't shaped by any single force, acting in isolation. It's shaped by the combined, intertwined influence of cosmic evolution, unfolding at the scale of stars and galaxies, and planetary geology, unfolding much closer to home, in the rock and atmosphere and orbital mechanics of our own small world. Neither force tells the whole story on its own. Together, woven across billions of years, they write something far more intricate, and far more genuinely fascinating, than either one could produce alone. And this brings us, gently, back to where this particular thread of our story began, the sun itself, and the final chapter awaiting it, once its red giant phase eventually draws to its own close. After the sun completes this dramatic transformation, after it has expanded enormously, shed a substantial portion of its own mass, fused helium into heavier elements deep within its core, and cast its outer layers outward into the surrounding darkness of space, what remains behind is something remarkably small, and remarkably different from the star we know today. The sun is expected to end its life not as some dramatic, explosive supernova, the kind of stellar death reserved for far more massive stars, but as something quieter, and in its own way, stranger, a small, dense, slowly cooling stellar remnant known as a white dwarf. A white dwarf represents, in many ways, the final, settled state of a star like our sun, once all the dramatic transformations of its life are finally complete. No longer generating energy through fusion, no longer capable of the kind of dramatic expansion and contraction that characterized its red giant phase, a white dwarf simply exists, quietly, as an extraordinarily dense, extraordinarily hot remnant, roughly the size of Earth itself, despite containing a significant portion of the sun's original mass, slowly radiating away its remaining heat into the surrounding darkness, over the course of trillions of years yet to come. There is something quietly fitting, and even a little tender, in this particular ending. The sun, which has spent billions of years pouring out light and warmth across the solar system, sustaining, for a time, the extraordinary complexity of life here on Earth, doesn't end its story in violence or destruction. It ends, instead, in a kind of long, slow, dignified fading, shrinking down to something small and dense and quiet, continuing to glow faintly, for an almost incomprehensible stretch of time yet to come, long after every planet that once orbited it, in whatever form they ultimately take, has fallen silent in its own turn. We're nearing now the final stretch of this long, patient journey we've been tracing together tonight, from the very earliest chapters of Earth's story, through the slow brightening of the sun, through the loss of oceans and atmosphere and complex life, all the way to this quiet, settled ending, a small white dwarf, glowing softly in the dark, all that remains of the star that once made everything else in this story possible. Let this settle gently, for now, as we prepare to carry this thread forward, one final time, toward the very last chapter still waiting ahead. We left the sun settling into that quiet, glowing remnant, a small white dwarf, all that remains of the star that once made everything else in this story possible. Let's spend a little more time with that remnant now, because there's something genuinely astonishing hidden within it, something that's worth sitting with slowly, before we bring this long journey to its close. A white dwarf may be roughly the size of Earth, but the similarity ends almost entirely there. Because packed within that Earth-sized sphere is an amount of material so dense, so extraordinarily compressed, that ordinary intuition struggles to make sense of it. Consider this. A single teaspoon of white dwarf material, just a small, ordinary spoonful, would weigh approximately 5 tons. 5 tons, in the space of a teaspoon. That's roughly the weight of an adult elephant, compressed down into a quantity of matter you could stir into a cup of tea, if such a thing were remotely possible to hold. It helps, perhaps, to understand where this almost unimaginable density actually comes from. Once a star like the Sun has exhausted its nuclear fuel and shed its outer layers during the red giant phase, what remains is essentially the star's core, no longer supported by the outward pressure of ongoing fusion. Without that fusion holding it up, gravity compresses the remaining material inward, dramatically, until the atoms themselves are packed together far more tightly than in any ordinary matter we encounter in everyday life. The electrons within those atoms end up crushed so closely together that an entirely different kind of physics takes over, a quantum mechanical pressure that finally halts the collapse, holding the white dwarf stable at this almost impossibly compact size. The scale of this compression becomes even more striking when we consider just how much mass gets squeezed into that small space. A white dwarf can contain something close to the Sun's entire mass, that vast, glowing sphere we see in our sky today, more than 1,000,000 times larger in volume than Earth, compressed down into a remnant roughly the size of our own planet. It's a genuinely difficult thing to picture, an object carrying the mass of an entire star, condensed into a volume you could, in principle, walk across in a matter of hours, geologically speaking, the way you might cross a modestly sized continent. And what, precisely, is this densely packed material actually made of? The Sun's future white dwarf core is expected to be composed mostly of carbon and oxygen, elements forged deep within its interior during the later stages of its life, as helium fusion proceeded through the red giant phase, building these heavier elements atom by atom, layer by layer, over the course of that dramatic transformation. In a strange and quietly poetic sense, the Sun's final form will be built from the very products of its own long life's work, carbon and oxygen, elements essential to nearly every complex molecule found in living things, elements that made up so much of the life that once flourished, briefly, on the small planet orbiting nearby. Given this composition, and given the almost complete absence of any ongoing fusion, it's worth clarifying something that might otherwise seem contradictory. If a white dwarf isn't generating energy through nuclear fusion any longer, why does it still shine at all? The answer lies simply in leftover heat. A white dwarf shines not because it's actively producing energy, the way the Sun does today through hydrogen fusion, but because it remains, for a very long time, extraordinarily hot, a residual warmth left over from its earlier, more active life, slowly radiating outward into the surrounding darkness of space. It's a bit like a coal pulled from a fire, no longer burning, no longer producing new heat, but still glowing steadily, still warm to the touch, for a good while afterward, simply because it hasn't yet had time to fully cool down. For a white dwarf, though, that cooling process unfolds across a genuinely staggering length of time. Because these objects are so dense, and because they have no ongoing fusion process generating fresh heat, they cool exceptionally slowly, gradually fading from a hot, bright white, through progressively dimmer and cooler shades, over the course of not millions, not billions, but trillions of years. The white dwarf that our sun eventually becomes will still be glowing faintly, however dimly, long after every other event we've discussed throughout this entire journey tonight has already passed into the deep, distant past. This returns us, one final time, to Earth itself, and to a possibility we touched on briefly in our previous chapter, one worth revisiting now, in this final quiet stretch of our story. If Earth does manage to survive the sun's red giant phase, avoiding outright engulfment through that delicate balance of mass loss and tidal drag we explored earlier, it may spend the remainder of its existence orbiting not a warm, life-giving star, but this faint, slowly cooling white dwarf instead. A frozen, airless rock, tracing its familiar path through space, around a small, dim ember of a star, illuminated by only a fraction of the light and warmth it has always known. And even this, it turns out, may not represent Earth's truly final chapter. Some estimates suggest that Earth's ultimate physical destruction, if it comes at all, might not actually occur until vastly later still, long after the sun has already settled into its quiet white dwarf state, drifting through a solar system that has already fallen almost entirely silent and still. Whatever eventually brings about Earth's final ending, whether through some slow orbital decay unfolding across further trillions of years, or through some other process still being explored by researchers today, that ending may lie so far beyond the sun's own red giant transformation that it becomes almost a separate story entirely, a coda added long after the main narrative of this solar system has already reached its natural close. As we bring this long journey to its end, it's worth gathering together, gently, the deeper thread that has run quietly beneath everything we've explored across these hours together tonight. Earth's long-term future, as we've traced it, fact by fact, chapter by chapter, is never shaped by any single force acting alone. It is shaped by cosmic evolution, the slow brightening of a star, its eventual transformation into a red giant, and finally, its quiet settling into a small, dense, fading white dwarf. And it is shaped, in equal measure, by planetary geology, the particular chemistry of Earth's rock and atmosphere, the pace of its carbon cycle, and perhaps most fundamentally of all, the slow, patient cooling of its own molten interior, a process that determines how long this planet continues to hum with active geology, long before any star ever forces its hand. Earth's future, in other words, was never written by astronomy alone. It has always been a story told jointly, between the vast, indifferent physics of a burning star, 93 million miles away, and the intimate, internal physics of a small, rocky world, still slowly losing its own primordial heat, 4.5 billion years after it first formed from the swirling debris of a young solar system. And woven through every part of this story, we've encountered genuine, honest uncertainty. Whether Earth itself ultimately survives the sun's red giant phase remains, even now, an unresolved question, one that continues to occupy careful researchers, refining their models, year after year, as our understanding of stellar physics and orbital mechanics continues to deepen. And reaching further still, beyond even that question, lies another, stranger uncertainty, whether proton decay will, given enough time, eventually unravel all matter in the universe itself, a question that touches not just on the fate of one planet or one star, but on the ultimate nature and permanence of everything that exists. These open questions are not gaps to be embarrassed by, or shortcomings in our understanding. They are, in their own way, some of the most honest and beautiful parts of this entire story. They remind us that even science, for all its careful precision, approaches a story this vast with genuine humility, offering not a single, rigid prophecy, but a rich, evolving landscape of careful possibilities, each one grounded in evidence, each one still open, in some measure, to revision and discovery. And so we arrive, finally, at the close of this long journey we've shared together tonight. We began with a single, quiet fact, that Earth, right now, has already lived through roughly 82% of its expected habitable lifetime, and from there, we followed the threads of that story outward, through the slow brightening of the sun, through the fading of oceans and forests and breathable air, through the delicate, uncertain dance of a planet caught between an expanding star and its own weakening gravity, and finally, into the deep, quiet stillness of a white dwarf, glowing softly, for trillions of years, over whatever remains of this small, rocky world that once, however briefly, in the vast scale of cosmic time, held oceans, and forests, and skies full of birds, and, for a little while, minds curious enough to wonder about all of this in the first place. It's a strange comfort, in its own quiet way, to hold a story this vast in mind, right before sleep. Because against a timescale of billions of years, the particular worries of a single day, a single week, even a single lifetime, settle into their proper, gentle proportion. Nothing about tonight's story is urgent. Nothing about it demands anything from you, right now, except perhaps this, a few quiet moments of wonder, before you drift off, held loosely in the very long, very patient arc of time that carried this whole story, from a molten, newborn Earth, all the way to a small, cooling ember of a star, so many billions of years from now. Rest now. The story will still be here, unfolding exactly as slowly as it always has, whenever you next return to it.